Okay, so yeah, we're just gonna move on. So last time we ended with here with ESP, right? But anyway, ESP, extrasensory perception, these are, well, fake. These are just magic, maybe some tricks. So anyway, they cannot undergo a laboratory experiment or laboratory test. Okay, so go to vision, and I believe you guys have finished your reading. If that's the case, then yeah. So first, light waves, 400 to 700 nanometers. You need to be familiar with all the wavelengths and their colors, okay? Wavelengths and colors. So to remember these, we use Roy G. Bibb, which is and mnemonics for rainbow, right? This is for rainbow: red, orange, yellow, green, blue, indigo, violet. Okay, and they correspond, like the range of colors corresponds to the light spectrum here. Okay, so red has the longest wavelength, and then violet has the lowest wavelength. Okay, if that makes sense. Light are basically just waves, right? So for waves, we have two properties or two attributes to describe the wave. Okay, one is amplitude and the other one is wavelength or frequency. Okay, so amplitude refers to the difference between the maximum and the minimum. So how large they amplify, how large they go top and down. Okay, and then for wavelength, it's just the length between one crest to another, or the length between one trough to another. Okay, and wavelength is the same as, it's not the same, but it's similar to frequency, because shorter wavelengths gives you higher frequencies, and higher frequencies and longer wavelengths give you lower frequencies. Frequency refers to how many cycles the wave oscillates in a second. Okay, so frequency is number of cycles this wave oscillates in a second. So cycles per second. Cycles per second is a unit, and we call it hertz. Okay, Hz, hertz, like this. Okay, it's named after a scientist whose last name is Hertz. Okay, so if we say 10 hertz, that means the wave oscillates 10 times in a second. 100 means 100 times a second, and so on. Okay, so the shorter the wavelength is, the higher the frequency it is. Okay, and that's because, for example, if you compare these two, this is a shorter wavelength, this is a wave that has a longer wavelength, right? So if you think about the time, let's say this is 1 second. So for shorter wavelengths, you see it oscillates 1 cycle, 2 cycle, 3 cycles, right? So for the top one, you could say it has a frequency of 3 hertz, 3 cycles per second. For the bottom one, it's roughly just 1 and a little bit, maybe like 1.2 hertz. Okay, so the longer the wavelength is, the longer it takes to cycle once, right? So lower frequency. The shorter the wavelength the wave has, then the shorter amount of time it takes to cycle once. Okay, so that means it has a higher frequency. In a given period of time, it can cycle more than the other wave. Okay. In physics, you will learn about the relationship between the wavelength and frequency. So, Cloman, have you taken a physics class yet?
I finished it last semester.
Okay. Are you familiar with the formula between wavelength and frequency?
Is it like period?
Period.
Or is that like lambda?
Lambda, yes, it's lambda. Lambda equals what?
F over, wait. Lambda equals to,
1 over F.
oh, right.
Yeah, 1 over F. Okay. So Torres, have you learned this formula? Yeah. No? Okay, this is in physics 11, I believe. Okay. So lambda is the letter we use to notate wavelength. Okay. And F is a letter is a notation for frequency. So their relationship is basically an inverse relationship. So lambda equals the reciprocal of frequency. So that's why the shorter the wavelength is, that meaning that the lambda, if lambda goes down, that means frequency goes up, right? Because the bigger denominator is, the smaller the value is, right? So frequency goes up, denominator goes up, lambda goes down, wavelength goes down. If frequency gets lower, frequency drops, then the denominator becomes less and less. That means lambda goes up. You see? Okay, a reciprocal relationship. Okay, anyway, we don't need to know the formula here, just to understand wavelength and amplitude and frequency. So now wavelength is the color, which is called hue, and amplitude is related to intensity, and in the case of vision, in case of light, it represents brightness. Okay. There's no question. Let's go to the structure of the eye. I already have everything labeled. So yeah. So if you guys have read a book, do you guys have any question about the structure of the eye? Cornea, iris, lens, pupil. You're gonna understand the functions and the location of each thing.
How significant is this like on the exam?
How is what?
How significant is this, like the eye?
Most significant. Well, the entire chapter 4 occupies around like 10%. If you look at those parents' book, about 10, 8 to 11, like 9 to 11%. So yeah, it could be multiple choice questions that ask about each thing. Yeah, maybe a function of a structure here, maybe something, maybe one to two multiple choice questions. Maybe there are, maybe there aren't, but that doesn't mean that you should overlook it, right? Okay. Yeah. But is there any question about any part of the eye? Okay, if there isn't, I'm gonna mention a few things. First, retina is where transduction happens. Do you guys remember what transduction means? What is transduction? We mentioned in last class. Okay, transduction is to convert from physical energies to neural impulses. Remember, from sensation to perception, okay? Your sensation. So from light to neural impulses, or from sound to neural impulses, from any physical energy to neural impulses, to signals that your brain can understand. This process is called transduction, okay? So transduction has appeared in previous exams a lot of times, okay? Again, because this is not an ordinary word. It's not a word in daily use of English, okay? So transduction, so for vision, retina is a place where transduction happens, meaning that retina converts from, well, light waves that we just saw, light waves, right? Convert light waves into neural impulses into electricity, okay? And specifically, the transduction sites are cones and rods, right? Cones and rods. If you have done the reading later, you will see that. Yeah, so just this, and then blind spot the reason why we have a blind spot in our eye is that that's the place where the optic nerve leaves the eyeball. Okay, and again, we have seen questions like these in previous exams. Okay, blind spots. The reason why we have it is that you have your optic nerve leaves or exits the eyeball there. So at that point, at this juncture, you don't have any retina there. Okay, so no transduction could happen there. You couldn't see anything at that spot. Okay, so if that makes sense, I'm gonna move on. Accommodation is the process that your lens change its shape and thickness, changes curvature, so that you can focus whatever you need to see onto your fovea. Okay, onto your fovea. Fovea is right here. Fovea is a point of central focus. Fovea gives you the best clarity, the best what we call visual acuity. Visual acuity. Okay, visual acuity. And nearsightedness has an academic term. I believe you should make yourself familiar to it. Okay, myopia. Myopia is just academic term for nearsightedness. To change it to an adjective, you change the A to C. Myopic is the adjective for it. Nearsighted. Farsightedness. Farsightedness is called hyperopia. Okay, hyperopia or hyperopic. That's its adjective. Hyperopia. All right. Rods and cones and ganglion cells. So, so this is what your retina looks like. Okay, there were 3 layers of cells. The first layer is rods and cones. So this is the first layer, rods and cones. So again, rods and cones are where the transduction happens. Transduction, okay, the process by which the sensory neurons convert physical signals into neural impulses. Okay, so rods and cones convert from light into neural impulses. Okay, and after cones and rods, they transmit their signals into the second layer of cells, and they are called bipolar cells. And the bipolar cells transmit the information into the third layer, which are called ganglion cells. Okay, ganglion cells are rarely tested. It's pretty complicated. You don't have to know. For bipolar cells, for these 2 layers, you don't have to know the exact function of them. Okay, you just need to know, well, they exist. And then for bipolar cell, it has a very unique visual appearance. Okay, so that's something you need to know. The reason why it's called bipolar is that, well, it has 2 poles. So usually, if you recall, a neuron looks like this. So this is a neuron, this is the axon, right? And axon branches, axon terminals. And then the other side, you have dendrites, right? Dendrites are grown on the cell. So like this. And these are dendrites, dendritic branches and stuff, right? Okay. But for bipolar cells, the dendrites are not directly on the cells, but they are sort of protruded out, and they have a similar visual appearance as the axon. So bipolar cells, you have an axon, and then for dendrites, you have something similar to the structure of the axon. So that's why we say it has 2 poles. Okay, does that make sense? It's called a bipolar cell. The question might ask you what a bipolar cell looks like, or it might ask you where we can find bipolar cells. So for where it's in the retina. Okay, in retina we can find bipolar cells. And for what it looks like, it just looks like this. Okay. So choose the appropriate description of the shape or of this feature, and that'll be fine. Any question for bipolar cell? Okay, for ganglion cell, yeah, we will see that later. It's in the color vision theory. Okay, we will see that. But anyway, so cones and rods. Yeah, so for blind spot, you can do a little demonstration to see it. And also, rods and cones, they are collectively called photoreceptors. It's on your book, okay? It's page 515, all right? They're called photoreceptors. Photo is a root word for light. So photoreceptors literally means light receptors. They receive light and convert it into neural impulses. Okay. Cones are much, well, there's a chart here comparing between cones and rods. Okay, so let's look at these and then talk about their functions. Okay, rods outnumber cones by like 20 times. You see, so there were a few cones, you could say, compared to rods. There were many rods. Cones cluster around the fovea. So the location of cones in retina is in the center, which is the fovea. Okay, so basically in the fovea we have nearly all of them being cones. Okay, and outside of fovea, nearly all of them are rods, periphery, on the periphery of the retina. So that's why rods are much more than the number of rods is much more than the number of cones. Because remember, fovea is only a tiny little part in your retina. Okay, so here, let's go back to the structure again. Okay, fovea is just a tiny little part in your retina, right? So in the fovea, we have cones, and outside of fovea, we only have rods. So that's why we have much more rods than cones. Okay, make sense? And fovea is to focus your vision. It has the greatest visual acuity. So we know that cones are there. So cones are very sensitive to details. Okay, so detail sensitivity, or in other words, visual acuity for cones is very high. For rods, those are pretty low. Okay, and the cones can also tell what color you have. The reason why we can see colors is because of cones. Okay, cones can detect colors. To detect colors, you need light. Okay, because the reason why you can see different colors is that light is shed upon objects. Okay, and different objects reflect different lights and absorb the other light. So for example, the reason why, say, the reason why the apple is red is that you have light shed upon the apple, and the surface of the apple absorbs all the other light except for red, and it only reflects the red light. Okay, it only reflects light of wavelength that are 700 nanometers long. Okay, so it absorbs all the incoming light. It only reflects red light. So that's why you can see an apple being red. Okay, so to see colors, you need light. Imagine that you have very dim light. Say that you are on a dark street, okay, in the night. You can't really tell what the color, like what the color are the cars on a dark street, right? If you think about it, if you haven't really noticed this, maybe the next time, if it's evening or the middle of the night, if you're walking on a street, try to tell the color of the incoming cars. You will see that it's pretty difficult. all the colors look pretty gray and dark and darkish to you. Okay, that's because of the lack of light. So for cones, they work better in bright light, and they work really bad. They work really they don't really work in dim light. Okay, they only work in bright light, and they can help see colors. They can help see detail. Okay, and for rods, they are basically their functions are basically to tell brightness for you. Okay, to do black and white, to tell brightness. So they work very good in dim lights. So that's why in the night you can still see things. You're just not able to tell the colors. Okay, so you're still able to see things. So that thanks to rods. Okay, they are not accountable. They don't account for color vision, and they are not really good at perceiving details. Okay, any question about the differences between cones and rods? To understand this detail sensitivity or visual acuity, you can use this book as an example. So say that you can look at this word, special, okay? If you just focus your vision on it, you will see that, well, you are able to read this word, but if I ask you what this word is, say this word, while looking at this word, it's very hard to tell what other words look like, right? Can you read a book with your eyes focusing on one word? You can't, okay? So yeah, so that's what we meant by visual acuity. So if you look at this word is directly projected onto your fovea. Remember, by your lens, okay? Your lens, bend the light such that the light of this word goes into your fovea, and all the other words, they go to your periphery, go to the periphery of your retina. They don't go to your cones. They don't go to your fovea or your cones. They go to your rods, and rods can't really see detail. So that's why you're not able to read the other part of the page if you focus your eyes here. Okay, make sense? Visual acuity or detail sensitivity. Yeah, okay. Yeah, and the reason why cones can bear such high detail sensitivity is because of the bipolar cells. Okay, remember bipolar cells? They look like this, right? One axon, one dendrite. So cones transmit their information to bipolar cells one to one. Okay, every cone transmit their messages to one bipolar cell. So that's why they have a much higher detail sensitivity. For rods, hundreds of rods. So a lot of rods, they send their messages into one bipolar cell. Okay, so that's why they bear a low sensitivity for detail. Does that make sense? Okay, it's in the book here. If one cone transmits its message to a single bipolar cell. Okay, so that's the reason for the detail sensitivity, and that's also one of the functions for bipolar cells. You don't have to know this, but it's not bad for you to know. Okay. All right, if that makes sense, we can move on to later. This is the organization of your visual system. Yeah, so okay, I should probably wipe this out and explain again. So your visual system, if you are looking at a focus, like here, okay, if you're looking at it, that's your focal point. To the left of a focal point is your left visual field. To the right of your focal point is your right visual field. Okay, the left visual field goes into your right hemisphere, and the right visual field go to your left hemisphere. again, is a contralateral design. It's an opposite design, okay? And the reason for this is that you have a crossover point here, okay? So the left visual field, it goes into the inner side of your left eye, and it goes to the outer side of your right eye. See, this is your pupil. Okay, this is where the pupil is. So the left visual field, the light coming from the left visual field goes into the inner side of the left eye, right, and goes to the outer side of the right eye. Okay. And notice that the inner side of both eyes will cross in the middle, and the outer side of the eye doesn't cross, okay? So the outer side of the right eye, it doesn't cross, so it stays in the right hemisphere. The inner side of the left eye, it actually crosses over so that it goes to a right hemisphere again. So that's why all the information in your left visual field will go to your right hemisphere. Does that make sense? Okay, the inner side crosses, but the outer side does not cross. And this is the main gist conveyed by this figure. Okay, and similar for the right visual field. So for the right visual field, it goes to the outer side, this is through the pupil, goes to the outer side of the left eye, and it goes to the inner side of the right eye. And again, the inner side crosses over, so the right eye goes to the left hemisphere, and the outer side of the left eye, it doesn't cross over. The outside doesn't cross over. So the outside, the left eye, the outside of the left eye still stays in the left hemisphere. So that means both information, both visual pathway will go to your left visual field. So yeah, so left hemisphere, okay? So the right visual field goes to your left hemisphere. Okay, and then in the end, the middle thing, the crossover part is called chiasm, okay? Optic chiasm. The whole nerve is called the optic nerve, right? So the optic nerve crosses in the middle, and that part is referred to as the optic chiasm. Chiasm just means X, just means cross. Chiasm is the Greek letter X. Okay, Greek letter X, so it means cross. So just an optic cross, optic X, okay? And on their pathway, on the middle of the pathway, they go to thalamus. And that's, yeah, you just need to remember that they go to thalamus. Again, to review the function of thalamus, right? Thalamus, they receive all the incoming sensory information and transmit them into the appropriate brain regions, okay? So it's like a relay center, where it relays all the information. The whole organization is contralateral, okay, contralateral. Okay, any question about the visual, like the organization of visual pathway? Okay, you need to remember the chiasm. And remember that they go through thalamus, and remember that they have a contralateral design, okay? All right, okay, move on. So color processing. There was two theories for color processing. The first one is trichromatic theory. It states that we have three types of color receptors. We have basically means that we have three types of cones, okay? Because color receptors are cones, right? So we have three types of cones. One is most sensitive to red. Another is most sensitive to green. And the last one is most sensitive to blue. Okay, trichromatic theory states that the reason why we can see colors is because we have three types of cones. Each one is most sensitive to one of the colors here, red, green, and blue. Any question for this? It's a rather simple theory, okay? So it is true to a certain extent. So we actually, after we have those microelectrode and advanced technology and stuff, we confirm that we do have 3 types of cones in our eyes, okay? Now animals might be different, okay? Some animals, they have 2 types of cones. Some of them have one, some of them have none. And some of the birds, they can have 4 and even 5 and even 6 types of cones. Okay, so to them, maybe the world is more colorful than the world we see. And of course, for animals who only have like maybe 1 type of cone or even none of the cones, then their world is basically black and white. Okay. And the reason why we can see other colors is simply, well, the addition of different colors, like red and green, we can see yellow, whatever. This is the trichromatic theory. But it is also insufficient to explain another phenomenon. Before we go over there, we talk about, this is color deficient vision, okay? So color blindness can also be explained by the trichromatic theory. Okay, the reason why we have color blindness is that, well, some people, they lack one of the type of they lack one type of a cone. Okay, some people, they don't have the cone for red. Some people, they don't have the cone for green or blue, and that will make them colorblind. Okay. All right, here comes the important stuff. The reason why trichromatic theory isn't entirely correct is because of this phenomenon. This phenomenon is called after image. Have you guys done this while you read the book? You really should try this. It's a very interesting and amazing phenomenon. Okay. The idea is that if you stare at this image for about a minute or so, and then you just look at this spot, or maybe just look at your wall, okay? Choose a white wall of your bedroom and then look at it, and you will see an actual British flag, okay? So this is a British flag, but the color is, well, different. And it's very weird, right? But if you stare at it for a minute and look at the wall, you will see an actual British flag in the correct color. Okay, so similar after image, and search it in Google. It has a lot of demonstrations here if you want. There were some people, there were American flag. Okay, whatever. So if you stare at it again for a minute or so, yeah, and look at your wall, then you'll be able to see this after image. Okay, so in our after image, red, if you look at red for a long time and you look at a blank wall, you will see green, and vice versa. So if you see green, if you look at green for long, you will see red. Okay, if you look at blue for long, you will see yellow. If you look at yellow for a long time, you can see blue. And lastly, if you look at black for long, you will see white. And if you look at white for a long time, you can see black. Okay, so the pairing is red to green, blue to yellow, and white to black. Black and white. Okay, this is something you need to remember. Okay, red to green, blue to yellow, and white to black. Multiple choice questions might ask you what is the opponent color for one color. Okay, they're called opponent colors. Okay, is there any question about the after image phenomenon? You good? Okay, good. Now, this phenomenon cannot be explained by the trichromatic theory. You will see, trichromatic theory doesn't really have any way to explain why after image exists, right? Because the whole theory states that we have 3 types of cones, nothing we can use to explain the effect of after image. Okay, it doesn't really, it's not really able to explain why. So that's why we have another theory. And the other theory is called opponent process theory. So it's a very tricky concept. It's a very complicated process, but the bottom line is that we have these colors, and these colors are opponent colors, meaning that if you process red for long, green will rebound. If you process, say, yellow for a long time, then blue will rebound. And that's why you can see all the different, these opponent colors on a white space if you have stared at a color for a long time. Okay, sorry, 1 second. Hello? Afternoon? Oh, okay. 我现在还在影视，能来一会儿吗？可以的，好，行，好，谢谢啊。好。Okay. Yeah. So opponent process theory. Okay. This whole process, processing of opponent colors, happen in the ganglion cells. Okay, so that's why we have 3. Remember we have 3 layers of cells in the retina. Okay, so bipolar cells explain why cones are afford much better detail sensitivity than rods do. Okay, and ganglion cells explain the opponent process. You don't have to understand the exact process of how these colors are processed, why they're opponent colors, but you just need to know that they're opponent colors. If you process one color for long, the other one will rebound. So you will see that on a blank piece of paper or on a blank wall. Okay, and this whole process occurs in ganglion cells. Okay, so in the end, that we have to combine the 2 theories together to give rise to our best understanding of how visual system works. Okay, so color processing occurs in 2 stages. So first we have 3 types of cones. This fact has been verified. Okay, we have 3 types of cones, and each of them is the most sensitive to one of the colors. And then other cones, they are processed in opponent process cells. These cells are just ganglion cells. Okay, and they have those opponent processes: red to green, blue to yellow, and white to black. So this helps us explain everything, explain what we have found in retina, in cones, and also what in the after image phenomenon. Any question? Okay, so if that makes sense, this is a very important finding. It appears on exam for a lot of times, because you see the scientists who discovered this, they actually won a Nobel Prize. Okay, so feature detectors, they just specialized neurons that can detect features. Okay, I don't think it's hard, so If you have any question, let me know. If you don't, I'm gonna move on. One special type of feature detector, you could say, is the face area. So you have a fusiform face area in your brain that recognizes face. That's devoted to recognize faces. Okay, if you have any damage to this area, you will be unable to recognize faces. So you can recognize all the other shapes and objects, but not faces. So face blind, you could say. Okay, so if that makes sense, moving on. Remember, we talked about parallel processing and sequential processing, right? In vision, we have parallel processing. So in vision, for example, if you look at a bird, the color, the depth, the form, the motion of the bird are processed in parallel to one another, meaning that you can perceive all these aspects of your vision at the same time. Okay, parallel processing. In other words, it is also unconscious. Remember, parallel is to unconscious and sequential is to conscious processing, right? Okay, so it is unconscious. Whenever you look at something, you unconsciously and immediately know everything, every aspect of the vision you see. Okay, and the reason for this is again because of feature detectors. We have feature detectors for detecting features, but we also have diverse feature detectors for perceiving color, for perceiving motion, for perceiving every aspect of our visual signal, okay? So all of them are in your visual cortex, okay? And yeah, they process your visual signal directly, parallelly, in a parallel fashion, okay? All right, and one example of our parallel processing, conscious processing, is blind sight. Blind sight is very amazing. So blind sight refers to people who claim that they are blind but can still see. Okay, quote unquote see. So there were people who claim that they are. We have seen this phenomenon before, right? So yeah, so blind light manifest the two-track mind, okay? One conscious processing and the other is unconscious processing. So even though they don't have the conscious processing or the conscious awareness of what they see, but they can still be able to orient themselves in a room or whatever. So meaning that they're unconsciously, they're still processing the locations, of the objects, okay? Is there any question about this? Yeah, so a very simple summary of visual information processing. You first have Renault processing. You have rods and cones, and they send their messages to bipolar cells, and in turn they send their messages to ganglion cells, and ganglion cells, they form the optic nerve, goes into a brain, goes through optic chiasm, and then thalamus, remember, optic chiasm, and then thalamus, and go to your visual cortex. In your visual cortex, you have feature detection, you have, and also color detection, also motion detection, everything, and they've gone through parallel processing. So you can know every aspect of your visual information immediately, then directly, and at the same time. And in the end, everything gives rise to your conscious awareness. And all of these happen so fast that you don't really realize. They happen in around like 50, 60 milliseconds. And the processing speed is comparable to a supercomputer. Okay. Okay, so if that makes sense, we go to module 19. 19 is about Gestalt psychology, perceptual organization. Okay, so Gestalt psychology, this word Gestalt is a German word. It's a German branch of psychology. Gestalt is German word, means wholeness, or it means it just means whole. Okay, the whole idea of Gestalt psychology is that the sum is more than the whole is more than the sum of its parts. Okay, the whole is more than the sum of its parts, meaning that as we perceive visual information, we perceive it as a whole rather than just some of its parts. So, for example, this is a good illustration of the Necker cube. There were two ways to perceive this cube. One is that this edge facing out or this edge facing out. There are two possible cubes, yeah? Okay, you can perceive one or the other, and sometimes they switch. Okay, so this, the tourist,
No, I saw it in like this direction, and then I saw it in another direction, and I couldn't see it back, so I was trying to like see it back.
Yeah. Okay. Yeah, so this illustrates a lot of aspects of our visual processing. So first we perceive whole more than the sum of its parts. So the sum of its parts in this case will be just some circles, right? If you just look at the parts, they are just some circles with some space in the middle, right? But combined together, you can see a cube, and the cube can change its shape. So yeah, the whole is more than the sum of its parts. That's the very basic principle of Gestalt psychology. And Gestalt means whole. Okay. And it also illustrates that our visual consciousness is subject to moment change. Okay, it changes moment to moment. So you can either see one or the other, but yeah, okay. So it changes moment to moment. Okay, so the following perceptions are ways to perceive visual information in Gestalt psychology, principles of Gestalt psychology. Okay, I believe that most of the perception rules here are pretty easy. So if you have a question, to let me know. If you don't, I'm gonna skip. Okay, figure ground. Tell which is the figure, which is the ground. Right, reversible figure and ground. And then grouping, yeah, following principles. These are not all of them. There was something else, but yeah, for AP, you just need to know 3: proximity, continuity, closure. Any question? For depth perception, there were some cues that our eyes our brains are able to use in order to form depth perception. Okay, but because depth perception is extraordinarily hard, actually, because your retina is a two-dimensional world, right? Your retina only has two dimensions. It's a two-dimensional image, but somehow our brain is able to reconstruct the three-dimensional world from a two-dimensional signal. Okay, so how exactly does our brain reconstruct our two-dimensional signal to form a three-dimensional conscious awareness? And that's really hard. Okay, that's also the hardest part for like artificial intelligence vision system. There were like autopilot driving, the kind of thing. Those are, yeah. So if you wanna computers or robots to do the same thing, it's rather hard. Okay. So our brain uses some cues to perceive depth. There's an experiment here, visual clip. See if you have any question about it. Very easy stuff. No question? Okay, sure. Okay, I'm gonna move on. And then binocular cues, okay? Binocular cues are depth cues that require two eyes, require both eyes open. There are convergence, Reynolds disparity, yeah, and another thing is not mentioned, okay? Just convergence and Reynolds disparity. For Reynolds disparity, you can yeah, basically your two eyes see different things, right? Because of their locations are different, and your brain is able to tell the difference and know which one is farther away. For Reynolds disparity, the best way to illustrate this is that you can reach out your arm, okay, and use a thumb to point at an object far away, okay? So you can align, say you close one of your eyes, maybe use your left eye. You can use your left eye only and align your thumb to maybe say a tree farther away, okay? And after you align it, you change your eyes. You close your left eye and use your right eye, you will see that the thumb and the tree misalign. And then if you align your thumb and the tree using your right eye, and you switch to your left eye, and again they misalign. Okay, and you will see the Reynolds disparity. So two eyes see different things, but still your brain gives you a unified visual awareness, and your brain is able to tell the difference between your two Reynolds images and then calculate sort of calculate the distance of the object between you and the object. Okay, Reynolds disparity. Monocular cues, they're again pretty simple because they have all these illustrations, right? Okay, so is there any question about one of the cues here? You gotta remember all the cues and then be able to use them yeah, multiple choice question and also free response. Sometimes free response will ask you how we can apply one of the cues in a scenario. Then we move on. Yeah, most of them are pretty easy. And then motion perception. So motion perception, I believe I need to add something to it. Not to add, but to explain something, okay? So first, to perceive motion, of course, if something is moving, it's definitely, well, you can definitely perceive motion. And even if something is not moving, you can also perceive motion if I present a slideshow of 24 pictures a second, at least 24 pictures a second or 24 frames per second, you will see consecutive movement. Okay, and the reason for this, an example will be movies and cartoons and animations. Okay, anime or just animations or movies. Well, the screen is not actually moving, right? The screen is actually just showing you a bunch of pictures rapidly and successively so that you perceive motion with just some still pictures. We call each picture a frame, right? So if you ever heard of frames per second, it refers to this. If the playing speed is less than 24 frames per second, you will experience lags, okay? So if you play video games, you have definitely experienced similar effects, okay? When you play video games, sometimes it's lagging, right? It's lagging. You see your computer screen frozen and then you move from one screen to another, right? So yeah, so those are those could be due to your network condition or maybe your computer processor being slow, whatever, okay? It just, for whatever reason, your computer is delivering an FPS lower than 24, or sometimes just lower than 30, you will be able to experience a little bit of lag. Okay? The reason for this is that we need some time to process a picture. As we said, although it was pretty fast, it takes us around 50 milliseconds to process a picture. Okay, all the parallel processing and stuff. Okay, since it needs, we need 50 milliseconds to process a picture. If you present 24 pictures a second, that means each picture only presents itself less than 50 seconds, right? And after that, you see another picture, and after that, you see another picture. So that means before you have processed the first picture, the second picture is shown. So that means you process both pictures at the same time, okay? And the next picture. So that's why your brain, well, connects all the pictures together. So that's why you can see a movement. Okay, so phi phenomenon is something like this as well. So for phi phenomenon, you should Google it and see what it looks like. Okay, pi phenomenon is something like this. So here, this is what we call a GIF or GIF, right? GIF, a GIF. The reason why GIF works, and you can see motions. This one has overlap, maybe this. Okay, the reason why GIF works is that, well, GIF is actually just a series of still pictures. Okay, so for example, here, it's just a bunch of still pictures with each dot missing. But if you play it really quick and in succession, we perceive motion. We perceive that something is moving around, yeah? And that's how GIF works. And that's how animation works, how movie works as well. Okay, so is there any question about the frames per second and motion perception? Okay, good. Perceptual constancy. So perceptual constancy is an example of top-down processing. Remember, bottom up and top down. Top-down processing refers to a processing that involves your brain in it, right? Your brain basically constructs your perception. Okay, so perceptual constancy refers to that even if your retinal image is changing, you still perceive consistently of the same stimulus. Okay, so for example, something like this, if you look at the yellow part, this is bright, this is not that bright. Well, on your retina, this and this and this, all three sides, they should appear differently, right? But it does not affect your perception that all of them are yellow. Okay, that's perceptual constancy. Another example is this. So for different doors here, now they have different retinal images they have different images on retina. Okay, one is just a rectangle, but when you open it, it looks like a trapezoid, or, well, something that's not rectangular. Okay, but still, you're able to perceive that the door is always rectangle, even if it's always a rectangle, even if they change shape on your retina. Okay, so another example of perceptual constancy. Okay, does it make sense? Perceptual constancy. So it's a top-down processing. Okay, if our visual processing is entirely bottom-up, you will see that maybe in this case you will see that the door is not a rectangle, but everyone knows it's a rectangle, right? Another example, say that you go on a tall building, very tall building, and you look down to the roads, then all the cars appear very small, right? But still, it doesn't really make you to not perceive it as a car, right? Even if the cars on your retina, they're much smaller than they usually are, but it does not affect your perception that they are cars. Okay, again, you know what they actually are, and you know their actual sizes. and that's because of a perceptual constancy. This perceptual constancy is not natural. Okay, it's not something you were born with. If you haven't been trained in such a way, you won't be able to know. Okay, for example, researchers have found that if you go to Amazon jungles and if you study those Aboriginal people, they don't actually have, say, size constancy. They don't actually know objects farther away are smaller in their eyes. The reason why is that, well, they live in a forest, in a rainforest, and they have a bunch of trees and stuff. So in their whole life, they haven't really experienced objects farther away. So for them, if they see a buffalo very far away, you could bring them out of their forest, bring them to highways and stuff, and allow them to look at say buffaloes further away. Buffaloes appear much smaller than they really are if they are, say, 2 kilometers away, right? But they never get to experience this, so they don't know. They weren't able to tell they're buffaloes if they're 2 kilometers away because they're really small. If you tell them those are buffaloes, they don't believe it. Okay, they will say, well, buffaloes are really big, those are pretty small. Those cannot be buffaloes. But if you bring them closer, say that you drive a car, bring those Aboriginal people closer to the buffalo, and gradually those buffaloes become bigger and bigger. It actually it takes them aback. It surprises them to the extent that they actually need that kneel down and pray to their God. They found they as if they have seen something supernatural. Okay, even constancy depends on your experience. Okay, so this illustrates the
So do
concept.
animals think that too? Like if a dog sees me 100 meters away, they think I'm not a human.
If no, because normally dogs are, well, they experience this constancy, they experience depth perception normally, right? If you raise a dog, say in a box for maybe 2 years after it was born, then it would not have this constancy. Okay, but you're not able to know. But there were other experiments. For example, scientists have been trying to raise cats in an environment that doesn't have, well, stripes in it. So yeah, so they have done experiments like this. So this is a bin, okay, a bin. So they raise cats in a bin. So cats are here, cats, okay. Now they raise cats in a bin. They actually put a cover on their head so that the cats couldn't see their own bodies. And on the side of the bin, there were only horizontal stripes on the bin. Okay, only horizontal stripes on the bin. So the bin looks like something like horizontal stripes, horizontal stripes, horizontal stripes. There's no vertical stripe on the bin. So the cats have been raised in an environment without horizontal stripes in their entire life. Okay, if you do this for maybe a year, these cats lose their abilities to perceive vertical stripes. Well, they still retain the ability to perceive horizontal stripes. The reason why we can know is that if you bring these cats out of the bin after a year, okay, and if you give them, say, a pen, a pencil, okay, but if you give them a pencil horizontally, they will try to, they will reach out their paws and try to touch it, okay, meaning that they can see it. But if you give them a pencil vertically, they won't be able to see it. None of the cats raised in this fashion respond to a vertical pencil or pen or vertical stick. Okay, so that's how we know that they were not able to perceive this. So yeah, to answer your question, Torres, I don't actually know a similar experiment like that, but I believe if you raise dog in say in a box, and so the dog never experiences, well, objects farther away in this entire life, I don't think it can have depth perception, so farther away, they won't know that you are a person. Yeah, okay. But for dogs, even if they're surprised, it's not that easy to know, but maybe you can design experiment for that. Okay, but based on brain plasticities, dogs shouldn't be different than humans. Okay, we're both mammals, we have the same brain, basically. Okay. The principles of the brain is more than similar across species. Yeah, so those Amazon people really surprised psychologists. The first time we found this, psychologists were really amazed. Yeah, that they didn't even have constancy. They didn't even know further things appear smaller. Okay, yeah, so there were a lot of different constancy, but I just want to talk about like generally this process is top down and experience matters. Okay, and there were different constancies. You will see it's pretty easy to understand. Okay, brightness constancy, luminance, shape constancy, size constancy, yeah, etc. etc. Okay, so yeah, so in painting, if you want to paint something that has depth in it, you actually need to use all the constancy and all the molecular cues, combine all of them to construct a painting so that it shows depth, even if it's on a two-dimensional world. Okay. So say that you want to construct a painting that looks further away. What you can do is that, see, this is linear perspective. You can draw a small, maybe a little person here. I'm not really good at drawing, but maybe this is a small person, this is a bigger person. You see, even with this very simple drawing, you see, we perceive this as further away, this as closer to us, even if this whole thing is really, well, equivalently distant from you, right? It's just two-dimensional image on a screen, but you can still see further things and closer things. Okay, does that make sense? Yeah. Yeah, so the lack of constancy of Amazon Aboriginal people, and also if you guys recall, restored vision for young kids, like kids who are born without vision. Even if you restore vision to them, they won't be able to understand it. All of these tell us brain plasticity is important, right? Experience matters. Okay, so there's one philosopher we need to remember. Later on, when we go back to chapter 1, we will see him again. And this person, you have to remember him, John Locke. Okay, you just need to remember the last name Locke. Locke was a philosopher. He was among the first people. He was among the first few people who raised the idea, who brought the idea that our mind, our brain is well, is well developed, okay, with experience. What he said is that our mind is basically like a white paper, a blank slate, okay, when we were born. And then after that, our experience writes on it. Okay, we learn all of our things from experience. It's partially true, especially for, well, examples of restored vision and Amazon people, right? They don't have constancy. From all these examples, we can see that, yeah, this is true. And yeah, so that he was the first philosopher to bring this. That's what made him famous. Okay. You see, this idea was not that easy to raise. Maybe you think it's a pretty easy idea, right? Pretty intuitive idea. But before we mention all these examples, you wouldn't be able to know that something as simple as vision, as normal as size constancy or perceptual constancy require experience to learn, to really possess this ability, right? So it's quite amazing that he can, this Locke can bring this idea, you see, in 1690. So which is hundreds, no, a few centuries ago, he was able to foretell this. So back then was a pretty astounding idea or notion to the world. Okay. Yeah. So restorative vision, we've already talked about it. Perceptual adaptation. It's just something you can adapt to even if your vision is distorted. See if you have any question for this. If not, we will move on. And that's module 19. And move on to hearing. Okay, audition. So for hearing, we basically need to understand well, similar things as we have understood in vision. Okay, so in so hearing, so sound waves are also waves. They're just some movement of air particles in the air. Okay. Again, we have amplitude and frequency. So amplitude in sound waves represent, again, intensity. So intensity in sound means loudness, right? Loudness. So the greater amplitude is, the sound is louder, and frequency represents pitch. So higher frequency is well, it's to higher pitch. Okay, higher pitch is just like like women speaking, like like these are higher pitches. Okay, a low pitches is like you make your voice low, like this is low pitch. Okay, so yeah. So pitch is the frequency, loudness is the amplitude. The unit for measuring loudness is decibel. Okay, decibel. And this is the structure of ears. And see if you guys have any questions. Maybe I'm gonna just briefly go over the function. Okay. Just very briefly. Okay. So these are air waves, right? Sound waves. So sound waves enters your air. The first thing we'll encounter is the eardrum, and the eardrum, it's basically just a membrane, so it will vibrate in response to the to the air particle, to the sound wave, right? The sound wave, in essence, is just a wave. It's just an oscillation of air particles. Okay, so it will vibrate to it, and then connected to the eardrum, there were three bones, three little bones. Collectively, they're called ossicles. Okay, ossicle means little bones. Okay, they are hammer, anvil, and stirrup, but you don't have to remember these names. You just need to know there were three bones here. And by the way, there are three smallest bones in your entire body. Okay, so what ossicles do is that they amplify the vibration of the eardrum. Okay, they amplify the vibration about 15 to 20 times. Okay, and the bones will transmit the vibration into cochlea, and cochlea is where transduction happens for audition. Okay, again, transduction, remember? So for eyes, transduction happens in photoreceptors, in rods and cones, or you can say in retina. For ear, it happens in the cochlea, and specifically here, hair cells. Okay. And hair cells, they grow on basilar membrane. Okay, so your cochlea is something, it's like a snail. It's coiled, and if you uncoil it, in the middle you have a basilar membrane. It's like a skin, like a membrane, and hair cells grow on them. And the hair cells are like rods and cones. They transduce air fluctuation. They transduce vibration into neural impulses. Okay. And other than the cochlea, you have semicircular canals. Okay, semicircular canals are three circles. Okay, three half circles, because they're semicircular, right? So it's three half circles, and one oriented to up and down, one oriented to front and back, and another one oriented left and right. So it's like a three-dimensional structure. It provides you with a vestibular sense. Well, vestibular sense is that you know where and how your body moves. Say that in a car, you're accelerating or you're decelerating, right? You're going forward, you're going backward, you are experiencing brakes and gassing pedals. You will know, right? Even if you close your eyes, you will know. And the reason why you know is because of the vestibular sense made possible by semicircular canals. Okay. So basically, it's to know your body movement state. These are hair cells. Okay. So if you're exposed to loud noise, your hair cells might break. Okay, they might break, and then you will suffer from hearing loss. Okay, so two types of hearing loss: sensory neural and conduction hearing loss. For sensory neural hearing loss is that say that your hair cells are lost because you are exposed to very loud sound, then you experience sensory neural hearing loss. Or sometimes maybe you have an accident and it damages your auditory nerve. Okay, so sensory neural hearing loss is related to nerve damage. Okay, conduction hearing loss is related to the damage of, say, eardrum or the ossicles, okay, or the little bones. It's all because the eardrum and little bones, they are not neurons. They're just some structures that transmit vibration into the cochlea, right? Okay. If you have an infection in your middle ear, it might cause your eardrum to have a hole in it. Then you will experience hearing loss. Or maybe some sharp objects punctured your eardrum, or maybe as you grow older, your ossicles started to function worse. Okay, all of these can cause conduction hearing loss. And they have different ways to resolve. So if you have nerve deafness, you have sensory neural hearing loss, you can implant a cochlea, okay, an artificial cochlea into your ear. So say that you lost most of your hair cells, but you can still implant an artificial cochlea to restore audition. Like vision, it has a critical period, so that which means that if kids are born deaf and then you restore hearing later on when they're adults, they won't be able to understand sounds. Just like vision, remember, restore the vision. If it's too late, they won't be able to understand them because it has a critical period. Critical period is the best time window for an ability to grow, okay, to develop in your brain. If you passed the critical period and you haven't really learned it, and you haven't received any visual or auditory signals, then your brain will be unable to understand vision or audition ever again. Okay, so here, hearing pitches. I believe I need to explain both theories, because sometimes they can be hard to understand. And then some questions, yeah, they have, like these theories have been tested a lot. Okay, so for loudness, I'm not sure if you guys read this, but notice this part. Okay, the reason why we can perceive loud sounds from soft sounds is because of the number of activated hair cells, not the frequency of the hair cells. Okay, recall that from chapter 3, we have in action potentials. We learned that an action potential took around like 3 milliseconds to happen. Remember the action potential, something like this. You have negative 70, right, and go to negative 55, and go up to positive 40, and then go down and like this, right? The whole process took about 2 to 3 milliseconds. So that means within a second, a cell can fire around 300 to 500 times. 300 to 500 firings per second, okay? So hertz, right? Not hertz, per second. So action potentials per second. So that means for loudness, if you require them to hire more frequently, it's kind of hard. So it depends on number of hair cells. In our midterm, we had a similar question, if you guys remember. Okay, that's for loudness. Remember this, number of cells matters. So in perceiving pitches, it's roughly the same. We have two theory. The place theory says that different pitches trigger activities at different places in our brain, okay? In our cochlear basal membrane and then in our brain, okay? You just need to know that different places. So yeah, so different pitches, they stimulate the different parts of our brain and different parts of our cochlea, okay? This best explains sounds that have pitches over 5,000 hertz. Okay, our absolute threshold for frequency of sounds is between 20 hertz to 20,000 hertz. This is a threshold for pitch perception. Okay, so greater than 5,000 hertz can be explained by place theory. Okay, but most of our say sounds we hear are human voices, right? Human voices is between 1,000 to 4,000. 1,000 to 4,000. So men speak in about 1,000 to 2,000, and the women speak in about at a pitch about 3,000 to 4,000. Okay, so human voices are between 1,000 to 4,000. To perceive these, sounds of these pitches, we have another theory, frequency theory or temporal theory. Okay, for frequency theory, it says that basically if the frequency is 100 hertz, then we have 100 pulses per second. If it is 1,000 hertz, then that's 1,000 times per second. If it is like 4,000 hertz, there'll be 4,000 times per second. Okay, but we just explained that a cell can fire around 300 to 500 times per second, and even at extreme conditions, it cannot fire faster than 1,000 times per second. That's like the best they can do. Okay, and this will damage the neuron as well. So usually just around 300, 500, 700, something like that. Okay, so how do we achieve, say, 4,000 action potentials, 4,000 firings per second with neurons. Then we use the Volley principle. Volley principle. What Volley principle states is that, well, although for one single neuron, it's not able to produce stimulations or produce action potentials 4,000 times per second, but with multiple neurons, we can do it. And how exactly we do it? We're gonna space out the firings, okay? So each of the line here represents the time, okay, time. So say 1 second, or maybe just do 100 milliseconds, okay? Each bar can represent a firing, okay? So this is neuron 1, this is neuron 2, maybe you have more neurons, okay? So the first neuron, say, fire at this moment, and then the second neuron fire next to it, the third neuron fire next to it, etc., and maybe say that we have 10 neurons, and then neuron number 10 fire at this moment, okay? And after that, say after the 10th neuron has fired, the first neuron fired again. And this space between them, say this is 3 milliseconds, okay? So in 3 milliseconds, the first neuron can only fire, well, twice, right? The space interval between two firings is 3 milliseconds. But in the space between those firings, other neurons could fire, right? So it's sort of like a symphony, an orchestra, okay? They fire in succession, and yeah, so like this, the combined firing, the combined frequency can be well over 1,000 times per second. And this is called the Volley principle. Okay, see if that makes sense to you guys? So a sound that's, say, 3,000 hertz, it's represent, the reason why we can perceive this is that, well, in our ear, we have a lot of different neurons firing, together, but at different time space, they space out evenly, so that yeah, like a few neurons, maybe tens of them combined together gives you 3,000 times 3,000 actions potentials per second, and that's how you perceive 3,000 hertz sound. Okay. The frequency theory explains the best how we perceive sounds that are lower than 5,000 hertz. Okay, so greater than 5,000, we use place theory. Less than 5,000, we use frequency theory. And in frequency theory, we need to understand the Volley principle. This can be pretty hard. So it's like soldier alternate firing, right? Like these neurons, they alternate firings so that combined together, they have frequencies over 1,000 firings per second. Okay. So if that makes sense, locating sounds is, yeah, it's pretty simple, just a time lag. And yeah, okay, and that's module 20. For module 21, we have other senses. You need to know, I think they're pretty easy. Okay, I'm just gonna skip it. I want you to know that you have to understand the pain, okay? Understand the gate control theory of pain, and then understand the body position and movement. So vestibular sense, remember the vestibular sense, and yeah, and the body position. Yeah, so you just need to know pain, the gate control theory of pain, and this. The other ones are not that important. Just browse through them. For taste and smell, know olfaction and gustation. Just know the academic words for them. Gustation, olfaction, and yeah, just very simple material. Okay. So if you have any question for module 21, you can let me know. And that's all of unit 4. Okay, for your homework, I want you to continue reading into unit 5. And yeah, try to finish at least half of it. Okay, half of unit 5. Only 4 modules in unit 5. Try to at least finish 2 modules, and then if you have more time, maybe just wrap them, finish them all. Okay. Then do the questions in the book. Mark your questions. If you have any questions during reading, mark them up, and ask me during classes. Okay.